And before I hand it over to Dr. Rinovia, I would like to invite the Dean of Faculty of Mathematics and Natural Sciences, ITB, Professor Wahyu Sri Utomo, to give a welcoming speech. Professor Wahyu, time is yours. Yeah.
Thank you. Thank you, Prof. Edi. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone.
Salam.
On behalf of the Faculty of Mathematics and Natural Science, ITB, I warmly welcome you all to the Mathematics Distinguished Lecture Series held by Mathematics Department, particularly by Combinatorial Research Group. And I would like to express my thanks to Pak Joko Suprianto and all the heads of research groups in mathematics and all the heads of study programs in mathematics. Special thanks goes to Professor Edi Tribaskoro, Pak Edi, and Bu Rinovia, who have been ensuring and keeping this lecture series going on as scheduled and planned. And of course, I want to express my sincere gratitude to Professor Richard A. Brualdi from University of Wisconsin, Madison, USA. Welcome and thank you, Prof. Brualdi. Prof. Brualdi will be giving his lecture on permutation matrices, alternating sign matrices, and generalization. I hope that all of us will have a better comprehension regarding the matters that will be delivered. And I hope also that all the professors, lecturers, researchers, students, and participants from Indonesia and other countries as well in today's event will be having a fruitful and interesting scientific discussion. Again, thank you, Prof. Brualdi, and thank you to all of you. Please enjoy this lecture. Assalamualaikum.
Thank you very much. Thank you, Pak Dekan. And now let us have a group photo first. I invite Dr. Rudy to help us for that. So before to have a serious session, now we have photographers. Pak Rudy,
yes.
Please.
Okay, everyone, please open your camera. I have 4 pages of picture here, so I'll take all of them. Okay, here's for the first page. And then the second one. And then the third one. And this is the last one. Okay, thank you very much, Pak Edi. It's
okay, wonderful. Thanks, Pak Rudy. And now I ask Dr. Rinovia to chair this session. Please, Ibu Rino.
Okay, thank you, Pak Edi. So I would like to welcome everyone in this Zoom room to this Mathematics Distinguished Lecture Series. This is our last one in this year, but hopefully we will continue the lecture series next year. So it is my great honor to chair this session for Professor Brualdi. I would like to introduce him, although I believe that he doesn't need an introduction. We all know who Professor Brualdi is. So Richard A. Brualdi is, can you see the slide now?
Mm-hmm.
Okay.
Yeah.
So Richard A. Brualdi is a Professor Emeritus of Combinatorial Mathematics at the University of Wisconsin-Madison. And he graduated with PhD from Syracuse University in 1964. And then he started to lecture in University of Wisconsin-Madison at 1965. And he became a full professor in 1971 until 2008. And he was also the UWF Beckwith Bascom Professor of Mathematics in University of Wisconsin-Madison, and he is now an emeritus professor. Professor Buradi has 37 PhD students. I already graduated, I believe. He wrote 6 books and over 250 research articles. These are the 6 books that he wrote, and one of them is one of my favorite books, the one in the bottom right, The Mutually Beneficial Relationship of Graphs and Matrices. And Professor Buradi has received many awards and achievements. One of them is the Euler Medal from the Institute of Combinatorics of its application, and also prize for lifetime contribution from the International Linear Algebra in 2005. So I think without further delay, I will ask Professor Buradi to present his research result entitled Permutation Matrices, Alternating Sign Matrices, and Generalization. Okay, please, Professor Buradi.
Thank you very much. Do you have my?
Yes,
Oh,
I will share your slide.
Yeah.
Just a second. Sorry, I have a bit of problem here. Okay. Okay, so I hope you can see it now.
Yeah.
It's okay.
Yes. Is it okay? All right.
It's okay.
Okay.
Okay, so thank you very much for this kind invitation. I sort of always was interested in coming to Indonesia, to Java, to Bandung, but this will have to do as a virtual meeting here for me here in Madison, Wisconsin, and you there in Bandung. Next slide, please. Can you do the next slide? Sorry. So there is the basic outline of my talk. I'm going to talk about very basic things: permutations, permutation matrices, alternating sign matrices, and some other topics connected with that. Please, the next slide. So here is an aerial view of Madison, Wisconsin, where I am. As you see there, there's a peninsula. We're surrounded by 2 lakes there, Lake Mendota and Lake Monona. Madison is the capital city of the state of Wisconsin. It's also the home, of course, of the University of Wisconsin, which is the flagship campus. It has approximately 250,000 people. Excuse me, it's a great place to live. So here I give you a virtual Madison, Wisconsin there. Next slide, please. So please, we can ignore that slide. Go to the next one. That was just, go to the next slide, okay? It's a little awkward, but okay. So permutations can be modeled in 2 ways, okay? One as a listing of elements, usually taken to be the integers 1 up to n in some order, okay? And also as a permutation matrix, which I've given there for the permutation 3, 6, 1, 5, 2, 4. As you see, there is a 1 in the first row in the 3rd column, a 1 in the 2nd row in the 6th column, etc. Please go click again, please. Maybe if I just say click, that will make it simpler. So usually I'm just going to denote such a permutation matrix as you see there on the right. I won't put in the zeros, but I'll block the entries so that you can take it clearly where the ones actually lie. Click again, please. And if you actually go on to MathSciNet and put in permutations, you'll find that there are 31,000 or more hits. So it's a very basic concept. which has been certainly researched a great deal. Next slide. I'll just say next when I want next. Next, please. So a permutation consists of the integers 1 up to n in some order. And so some of the integers are out of order. So it's a question, how should we measure the out of orderness of a permutation? One way to do it is through the number of inversions. So if you take a permutation that I have there, go down, please, click. Okay. Then KP, KQ is an inversion, provided KP comes before KQ in the permutation, but KP is bigger than KQ. So it really consists of a pair of integers which are out of their natural order. And if you interchange those two integers, which are natural order, you get what is called a transposition. So if you look at that example there, you had a 1 in the 6th column of the 2nd row and a 1 in the 2nd column of the 5th row. There were zeros where you see zeros there. Next slide, please. And the transposition simply replaces that 0, 1, 1, 0, if you will, by the 1, 0, 0, 1, leading to the new permutation 3, 2, 1, 6, 5, 4. Next, please. So that's the base, it's a very basic idea of a permutation. Next, please. So a transposition, these are very basic things that I'm talking about, but if you're going to understand the way other talk, you have to make sure you know this. A transposition can always be chosen to reduce the number of inversions, but not necessarily the set of inversions. That's called I sigma there by 1. So if we do the transposition that you see there, where 2 and 3 are interchanged, it reduces the number of inversions. There originally were 4 inversions, 3, 1, 3, 2, 4, 1, 4, 2. And now there are just 3 inversions, 2, 1, 2, 3, I'm sorry, 2, 1, 4, 1, and 4, 3. So you can always choose a transposition to reduce the number of inversions. Now there's a special kind of inversion called an adjacent inversion. And that's where the two integers are adjacent in the permutation, KP and KP plus 1. You see that example that down there, 3, 4, 1, 2 becomes 3, 1, 4, 2. And the effect of an adjacent transposition is to remove one inversion. There was originally 3, 1, 3, 2, 4, 1, 4, 2, and now we got rid of the inversion. Which one did we get rid of? We got rid of the inversion, I can't find it there, 4, 2. That's no longer an inversion because 4 and 2 are in their natural order. So if there is it's very simple to check that if there is an inversion, then there must be an adjacent inversion. Now, let me remark a basic fact here, please. Next. A permutation of the integers 1 up to n is uniquely determined by its set of inversions. That's an easy introduction, basically, on the location of 1. But not in general by its set of inversions, adjacent inversions. So here's an example here. The permutations 4, 1, 2, 3 and 2, 4, 1, 3 have exactly one adjacent inversion. That's 4, 1. But they're different permutations, okay? Their sets of inversions are different, as you can see from that example there. So a permutation, as I say, once you know the total set of inversions, you know the permutation, but if you know the adjacent inversions, you do not know in general the permutation. So the question is, now, how can we compare two permutations other than by using the number of inversions? One can say, well, one has 3, the other has 5, 3 is smaller than 5, okay? But there is a partial order, in fact, 2 partial orders on the permutations, which I will discuss right now. Okay, next. All right. And the first of these is the so-called weak Bruhat order. Okay. And it simply says one permutation pi1 is less than or equal to another permutation pi2 in the weak Bruhat order, provided the total set of inversions of pi1 is a subset of the total set of inversions of pi2. So it really boils down to containment. Weak Bruhat order is simply containment of the inversions, okay? And one can show actually that this is equivalent to, you can get from pi2 to pi1 by a sequence of adjacent transpositions, each therefore reducing the set of inversions by 1. All right, so let me just say it again. If you have two permutations pi1 and pi2, and the inversions of pi1 are contained in the inversions of pi2, you can go from pi2 down to pi1 by a sequence of adjacent transpositions, and at each time reducing the set of inversions by 1. Now the second partial order, that's clearly a partial order because it's set theoretic containment. The second partial order is the so-called Bruhat order, okay? And this simply means pi1 is less than or equal to pi2 in the Bruhat order, provided you can go from pi2 to pi1 by a sequence of transpositions where each reduces the number of inversions by 1, but not necessarily the set of inversions. I think I have an example there, but I'm not sure now since I can't see it here. So please go to the, all right, I will give you an example. So what that means is that if pi1 is less than or equal to pi2 in the weak Bruhat order, it's certainly less than or equal to in the Bruhat order, okay, but not conversely. So, okay, so it's really set containment versus number. So let me, excuse me, I think I have an example here now, the next slide. As I say, I can't see these slides. So fine. So look at those two permutations on the top, okay? You see that you can go from the one on the right to the one on the left by one transposition, okay? You have 5 inversions initially, you can count them. It reduces to 4 inversions. So they're related in the Bruhat order, okay? But they are not related in the weak Bruhat order, okay? Because 2,1 is an inversion of the permutation on the left, but it's not an inversion of the one on the right, okay? So weak Bruhat order is really more restrictive, okay? It says weak, in some sense you might say strong, but it's weak Bruhat order because it's more restrictive, okay? So again, let me just summarize that the weak Bruhat order, okay, so here's an example, then that's fine. So this example I borrowed from a book by Bjorner and Brenty. I simply took a picture of it and then put it in my PDF file there, okay. So that's what the Bruhat order looks like for permutations of 1 up to 4. I just want to point out the permutation 4, 2, 1, 3. I think you can see it in the diagram. All right, and it is less than in this Bruhat order than 4, 3, 1, 2. You see a segment from 4, 3, 1, 2 on the left to 4, 2, 1, 3, right down there. So that is true. In fact, that covers in the Bruhat order. So that's what the Bruhat order on S4 looks like. Let's go to the next slide. Again, Bjorner Brenty book here. Okay, there is the weak Bruhat order. And as you see, that's less dense there. There's not as many relations in the weak Bruhat order as there was in the Bruhat order. And in fact, that permutation 4, 2, 4, 3, 1, 2, which was above 4, 2, 1, 3 in the Bruhat order is not in the weak Bruhat order. You've lost some relations in going from the Bruhat order to the weak Bruhat order, okay? So keep that in mind, okay? Weak Bruhat order is more restrictive because you got to do adjacent transpositions to reduce by 1 in stages, as opposed to Bruhat order, where any transposition that reduces by 1 is okay. Next slide. Okay, now the weak Bruhat order is actually a lattice. Every 2 elements have a least upper bound and a greatest lower bound, okay? And in fact, that's pretty, it's not entirely obvious, but you might suspect it given the fact that the order comes from set theoretic. So that is a, so I ask you, what is the greatest lower bound of 4312 on the top there and 4231? We'd have to trace it down to, it looks like 4123, if I'm not mistaken, down there. It's not too important, so, but you do have lubs and glubs, least upper bounds and greatest lower bounds in the weak Bruhat order. Okay, next slide, please. Again, I can't anticipate. So the Bruhat order, on the other hand, put the picture there, there it is again, is not a lattice, okay? So if you look at those permutations near the top again, 4312 and 4231, they don't have a greatest lower bound. Is it 4132, which is less than or equal to them? Or is it 4213, right to the right, which is also less than or equal to? But they're both greatest lower bound, so to speak, but they're different. So it doesn't have a greatest lower bound. So the Bruhat order is not a lattice, but the weak Bruhat order is a lattice. Next, please. Sorry. So here is the Bruhat order on the permutations of order 3. I've given it to you there both in terms of the permutations and the associated permutation matrices. And again, you see that this is not a lattice, because if you take the permutations 231 and 312, they don't have a greatest lower bound. It's not 213, it's not 132, because they're both bounds, lower bounds, but they're different and they're minimal or maximal, I should say. Okay, so this is not a lattice. So even already on 3 letters, 1, 2, 3, the Bruhat order is not a lattice. Okay, next slide, please. Okay, now in both of these orders, the identity is the smallest and the so-called anti-identity is the largest. The minimum has a unique minimal and a unique maximal in both cases. Next, please. Whenever you see stuff that's still there, you can actually go to the end of the slide. It makes it simpler. I mean, you can see that there's more to that slide. It's okay to reveal it since I can't do it myself. So the weak Bruhat order, sorry, you have to go back. The cover relation for the weak Bruhat order is simply they're less than or equal to, and you can get from pi 2 to pi 1 by removing 1 inversion. The Bruhat order simply says that the inversions of pi 1, okay, are contained in pi 2 and exactly 1 fewer inversion, okay? And both of these orders are graded by the number of inversions. The grade corresponds to the level in the diagram of the partially ordered set, okay, like so. Okay, so please, the next slide there. Okay, now, so if I give you two permutations and I ask you, are they related in the Bruhat order? Okay. What you would have to do is to come up with a sequence of transpositions that gets you from one to the other. And it's not obvious how to proceed in general by examining the permutations, okay? But there is a very easy algorithmic way to do this. And this is in terms of what is called the sigma matrix, sigma of A, okay? And sigma of A, you can define it for any rectangular matrix. The ij entry is simply the sum of the entries in the leading I by j submatrix. So there's an example there, A and sigma A. So for instance, the 10, the 2, 3 position of sigma A, that's simply the sum of the entries in the leading 2 by 3 submatrix of A, 1, 3, 2, 0, 3, 1, adds up to 10. And the important theorem is that the Bruhat order, P less than or equal to Q in the Bruhat order, can be checked simply by forming the sigma matrices and comparing them entry-wise, okay? If sigma of P is bigger or equal sigma of Q entry-wise, then P is less than or equal to Q in the Bruhat order. That is not obvious. That takes some work to do, but it's clearly very important because it says that you can do a simple computation, write a simple program just to compute these numbers and then compare them. Okay, so that's an important theorem. Next slide, please. I don't remember. Okay, now you can make one more click there. It's okay. Now there is a very important theorem due to McNeil, which was a generalization of the Dedekind completion of the rational numbers to the real numbers, but that's an infinite thing. I don't want to deal with that. But the Dedekind-McNeil completion is the following. You take, say, a finite partially ordered set, okay? Then there is a unique minimal lattice, the minimum number of entries, okay, containing the original partially ordered set, which extends the given partial order. Sorry, and that's called the Dedekind-McNeil completion of a finite partially ordered set. You can always make it into a lattice by adding a small number of elements, and the unique, with the minimal number, it's unique up to isomorphism, okay? So as I write here, if you have a favored partially ordered set, which is not a lattice, you can ask, what is its Dedekind-McNeil completion, okay? Any finite partially ordered set, there's a unique minimal lattice which extends it, okay? So, okay, so that's a very important theorem, okay? You can find it in many places, in particular in Birkhoff's old book on lattice theory. Next slide, please. So here's again permutations of order 3, back to, okay. It's not a lattice as we've already decided, so I'm just showing you this again. It's not a lattice because 2, 3, 1 and 3, 1, 2 don't have a greatest lower bound, just as 2, 1, 3 and 1, 3, 2 do not have a least upper bound, okay, like so. Okay, so just keep that in mind, okay? Next slide, please. Next, okay. So the question is, suppose you take the Dedekind-McNeil completion of the permutations of order n with the Bruhat order. What are the new elements going to be? There's a unique minimal set of elements that you can add to it in order to get a lattice, extending the original partially ordered set, okay? And very simply, if you look at those two permutations that you see there on the top, and the sigma 1 and the sigma 2, they don't have a meet, okay? If you take the minimum of those two, sigma 1 and sigma 2, you get 0, 1, 1, 1, 1, 2, 1, 2, 3, but there's no permutation matrix with that as its sigma. Because, why is that so? Because the fact that you, if I had something to point to, I could do that here. The fact that you have a 1 in the 1, 2 position and a 1 in the 2, 1 position has to tell you that the 1 in the 2, 2 position has to be 2 because of the summation definition there, okay? So the problem is that 1 in the 2, 2 position. But if I take, okay, this matrix here and put in a -1 there instead of that, well, what would be a 1 there, okay, you find that the sigma matrix is 0, 1, 1, 1, 1, 2, 1, 2, 3. You just do the advent. The problem is, of course, that -1, if this were a permutation, would have been 2, okay, but it's not, okay, like so. So that's what you get if you put that matrix, okay, next slide, please. So here is the Dedekind-MacNeille completion of permutations of order 3, okay? Okay, and in some sense, you would have suspected this before because those two things sort of crossed there, okay? But there wasn't anything there, okay? And so if we put that D3 there, okay, then you get a lattice. Now, the least upper bound of the two permutations on the lower part there is D3, okay? And the greatest lower bound of the two permutations near the top is also D3 there, okay? And that's a lattice. So that is what the Dedekind-MacNeille completion of the permutations of order 3 looks like, okay? You have to, and so what is the new matrix? You see it right there. That's what I call D3. That's what you have to add, okay? And then using sigma, the sigma construction in order to decide about one being less than or equal to the other. Next, please. How am I doing for time? It's getting, I won't complete everything, but that's okay. Next slide, please. Okay. Now, please write down, put out the whole slide there. Okay, right there. Whoops. Right there. So there's an important theorem of Lascaux and Schützenberzé in 1996, which characterized, defined, showed what the Dedekind-MacNeille completion of Sn, the permutations of order n in the Bruhat order is, okay? And there are two ways to describe it. One's in terms of their sigma matrices, okay? All right, and I'm not going to say what's there, okay? Because, but that's really what it is. That is, if you think of these in terms of the sigma matrix, that is the Dedekind-MacNeille completion of the permutations of order n with respect to the Bruhat order. That's version number 1. Version number 2, next slide, please. And again, put the whole thing up there if you can. A little bit more, go ahead, go down there. Okay, that the Dedekind-MacNeille completion is the set of n by n alternating sign matrices. Okay, these are 0, 1, -1 matrices where the plus minus ones in each row and column alternate, ignoring the zeros. Forget about the zeros, just look, I'll have an example momentarily. but it has to have a first non-zero as 1 and the last non-zero is 1. And so that's what and these include the permutation matrices because they don't have any -1. So this is certainly satisfied, okay? And the partial order is really a generalization of transposition, okay? All right, transposition, if you look down on the bottom there under note, okay? You can, and look over at the 1001 on the right, okay? If you add that matrix on the right to the one on the left, what you end up with is 0110, the middle one right there. Okay, so that is really transposition, except you're allowing some things to be -1. And when you do transposition on the permutations, everything stays 0, 1. But you can do transpositions, okay, on alternating sign matrices and also permutation matrices within the alternating sign matrices, okay, like that, okay. All right, and the alternating sign matrices can be gotten from the identity by a sequence of these types of transpositions with all intermediate matrices ASMs. So that is really neat, okay? The alternating sign matrices, which you see there, maybe you take it in partially, give you a partial order, which is a lattice and is the smallest lattice containing the Bruhat order on the permutations. All right, so this is the Bruhat order on the alternating sign matrices now. Next slide, please. And I don't know what, so here's examples of ASMs. Okay, you can see the matrix on the left. You look at the third row, forgetting the zeros, which are not listed there, you get 1, -1, 1, -1, 1. And if you go down the third column, you get 1, -1, 1, -1, 1. Begin at 1, end at 1, and alternate in between. Both the one on the matrix on the left and the matrix on the right, okay, like so. So they're very interesting objects, okay. Next slide, please. So do the whole slide, please. There are some basic properties there. The only thing I really want to mention here is that the alternating sign matrices are invariant under the dihedral group, the symmetries of the square. If you do any one of those symmetries, you get another alternating sign matrix, okay? Like so. The other properties are not too important so let's go on to the next one, okay? Next slide, please. Okay, and do the whole thing, and I'm not going to read this at all here. Simply that's saying, because presumably you're gonna, if you're interested, you can go back and look at my slides. I think they're probably being recorded somewhere. That this gives you the bijection between the two versions of the Dedekind-MacNeille completion. Remember, one was given in terms of sigma matrices, the other was given in terms of alternating sign matrices, and you can go from one to the other quite easily, okay? And in fact, if you look at the bottom there, it shows you how to get from the sigma matrix to an entry in the alternating sign matrix, just as you see there, okay, like so. Okay, so it's known, okay, and it's not so hard. So what's the Dedekind-MacNeille completion of the weak Bruhat order? I just described the Dedekind completion of the Bruhat order. The answer is it's already a lattice. Remember, the Dedekind-MacNeille completion is itself. You don't have to do anything to complete the alternating sign matrices using the weak Bruhat order. It's already a lattice. Nothing more has to be done. Okay, okay. Next, please. I don't know what's next. Okay, the whole slide, please. Just go down to the bottom of it. The combinatorics like to count things. So you know how many n by n permutation matrices there are, n factorial. How many ASMs are there? And it turns out there is a famous theorem first proved by Doron Zeilberger in 1996. And you see that formula there. It's not an obvious formula, very complicated formula, okay? Bunch of factorials in the numerator, a bunch of factorials in the denominator, but that is been enumerated. It knows how many there are, okay? And so for instance, for 4x4s, there are 42. And by 4x4 alternating sign matrices, and it goes up to 429 when you get to 5. Okay, so they grow rather rapidly. Excuse me. Next, please. How much time, Eddie, do you have? I have about 15 minutes.
It's your time, Professor Bruwardi. You have
Yes,
how
you
many?
have around 20 minutes actually, because we
Okay.
started late.
20 minutes.
Let
Don't
me
worry.
just briefly, because it's sort of interesting. These ASMs actually came up by physicists where they were called square ice, okay? And their square ice is simply a configuration of hydrogen and oxygen atoms, okay? Frozen in a square lattice. Next slide, please. So here is the array that I'm looking at. H is hydrogen, O is oxygen, okay? And there are twice as many hydrogens as there are oxygens, so that you can form H2Os, water molecules, okay? So we want to attach each oxygen atom to 2 H's in order to get a water molecule, and to do this in a 1-to-1 bijection, 1 oxygen, 2 hydrogen. And there are 6 possible configurations for the H's and the O's. Next slide, please. Okay, there are the 6 configurations, okay, that you can have in this pattern. And if you let the top left one, the horizontal configuration, correspond to 1, and the vertical one correspond to -1, and all the others correspond to 0, you get an alternating sign matrix. Next slide, please. Okay. So here's a configuration of the type that I'm talking about, okay? And you could see this is the H0H in the row on the top is a 1. Below there, the H0H vertically is a -1. And there's the alternating sign matrix that square ice configuration corresponds to, okay? It's a 1-to-1 mapping bijection between square ice configurations and alternating sign matrices. Very interesting. Next slide, please. Okay, I want to mention this here, and because I find it very interesting. Even you can ask, where do ASMs come from the mathematical literature? Okay, they came from something called the lambda determinant. Okay, so what is that? Okay, well, so you could start with, for a 2x2, it's what you see there, okay, the lambda determinant. That lambda, if that were a -1, would be the ordinary determinant. So you can start with that, or you can actually just start with the 1x1, as I've drawn there. Now, there is a famous theorem of Dodgson, the Lewis Carroll, okay, a condensation formula for determinants, which if you use iteratively, expresses a determinant in terms of 2x2 determinants. So look at that displayed equation you see there, okay? Make believe lambda is 1 for the moment, okay? Just forget about lambda, okay? And what that says is that the determinant of A, of an n by n A, is the determinant of the n-1 by n-1 in the upper left times the determinant of the n-1 by n-1 in the lower right, okay, minus, okay, the determinant of the n-1 by n-1 in the upper right times the determinant of the n-1 by n-1 in the lower left. It's like the determinant of a 2-by-2 matrix. Okay, upper, upper, lower, lower, upper left, lower, upper, okay? Divided by the determinant of that n-2 matrix in the middle, okay? n-2 by n-, so cross out the first row, second, last row, first column, last column, okay? So that's the definition of the lambda determinant, iteratively, okay? So very quickly, since I don't want to dwell on this, go on to the next slide, please. So here is what it is for n equal to 3 on the bottom of that slide, okay? Notice two things. One, if you let lambda equal -1, therefore lambda squared plus lambda is 0, you get the ordinary determinant. Okay, there's only one sort of strange term there, that one with the -1 exponent. All right, and if you take lambda equal -1, that disappears, and these permutations which have the lambda in front of them, or lambda cubed, will have the right sign. The lambda squared, of course, goes to +1. All right, so if lambda is -1, you get the next slide, please. And very quickly, put the whole slide there, okay? All right. If you take those terms there, all right, and now look at the exponents of the entries in that 7 terms that you have there, all right? Look at the exponents. So for instance, if you look at A12, A21, A23 there, okay, the exponents are 1, 1, 1, occurring at the permutation set of places 1, 2, 2, 1, 3, 3. And if you look at this thing with the -1 in it, you see that alternating sign matrix 3 by 3 in the middle. That -1 occurs on the 2, 2 entry. And the 1, 2 and the 2, 1 have a 1 exponent, and the 2, 3 and the 3, 2 have a 1 exponent, and the other entries don't occur. So you get that alternating sign matrix, okay? And it turns out that the lambda determinant is an expansion, let me just say that, over the alternating sign matrices, okay? There's a certain polynomial there in front of the terms, but each alternating sign matrix gives you a term. Each term corresponds to an alternating sign matrix. Okay, and the number of terms is, of course, the number of n by n ASMs. Okay, a large number of terms there. Okay, you can go to the next slide, please. Okay, so now I want to say, say the whole thing, go back one up, please. A few things about a topic which I've become interested in. This alternating sign matrix thing goes back about 10 years for me, where I first wrote a paper with then 3 of my current PhD students about 10 years ago. But this is something I've only become interested in the last couple of years, and that's avoiding patterns in permutations, okay? So avoiding a pattern in a permutation means that you cannot find terms in the same relative order as the pattern. So if you have a permutation sigma of length k, and you look at a permutation of order n, if you can find within pi k entries which have the same pattern as sigma, same relative order, then you say that pi contains sigma, otherwise it avoids sigma. Okay, so if you take k equal to 2 and the permutation 2, 1, to avoid 2, 1 in a permutation simply means no decrease. You can't 2, 1, no decrease. So the only thing is the identity. If you take 1, 2, and you want to avoid 1, 2, you have to avoid an increase in a permutation, only the anti-identity permutation. This is a very important topic. It's a very big topic. They have, as I mentioned there, they have a conference on this every 2 years. Okay, next, I've never been to one of these conferences, by the way. Next slide, please. Take the whole slide, please. So for patterns of length 3, so that means permutations of 1, 2, 3, there are 6 of them. There's 6 patterns, but up to equivalence, there are only 2. 1, 2, 3, and 3, 1, 2. Everything else can be gotten from the other by complementation and reversal, etc. Okay. So here's an example of a 3, 2, 1 avoiding permutation. You do not see, unless I've done this incorrectly, a decreasing subsequence of length 3. That's what it would mean to avoid 3, 2, 1. Okay, okay. I like to sometimes think as this is large, small, medium for 3, 1, 2. Okay, or like so. And as it turns out, so there are only 2 basically inequivalent ones, but they all give you the same number, the Catalan number. The number of permutations of order n that avoid any specific pattern of length 3 is the nth Catalan number. Okay, like so. These Catalan numbers arise, as you probably know, in lots of different ways. Go ahead to the next slide, please. All right. So here's I've given you a 3, 1, 2 avoiding permutation there. It simply says, if you think of these in terms of permutation matrices, you cannot have a 3 by 3 submatrix of the type that you see there, that 1, 1, 1, or what I like to think of, the largest column, the smallest column, the middle column, or the medium column, okay? That's what it would be to be 3, 1, 2 avoiding, okay? Now, this suggests the possibility, rather than looking at n by n permutation matrices, just ask this type of question about 0, 1 matrices in general. No pattern of the type that you see that I've got display there. I've done 3, 1, 2, okay? Okay, so n by n 0, 1 matrices that don't have a submatrix that looks like that 3 by 3 that you see there. Next slide, please. Excuse me. So here's an examples, okay? Those are 2 examples of matrices that don't have a 3, 1, 2, assuming I haven't made a mistake, which I don't think I did, because I think it's okay. And it turns out that such a matrix can have at most twice n plus n minus 2 ones. And if it had fewer than that many ones, you can always find another 0 to replace by a 1 and still have it to be 3, 1, 2 avoiding, okay? So everything can be increased to the maximum number. If you start with any 3, 1, 2 avoiding 0, 1 matrix, you can always bring it up to the largest possible there, okay? 2 times n plus n minus 2. Next slide, please. Now, okay, there's a continuous analog of permutation matrices. Some people don't like discrete mathematics. The doubly stochastic matrices. These are simply non-negative matrices square all the row and column sums 1. And by the famous well-known theorem of Birkhoff, that's the convex hull of the n by n permutation matrices. And these are the extreme points of that convex polytope. It's a bounded polyhedron because We're taking convex combinations of things. And it is a polytope of dimension n-1 squared, which really means that the set of n by n permutation matrices has a linear span of dimension 1 more, okay? Which means that there are bases of the n by n permutation matrices of cardinality n-1 squared plus 1. That's what a basis of the n by n permutation matrices is. Turns out there are several known bases, and the oldest one I found just by accident due to Farahad and Mirsky. It's kind of interesting. Here's what a basis is. The identity permutation, all the 2 cycles, okay, all the permutations which just consist of a 2 cycle and then fixed points, and then all the permutations which have this 3 cycle, 1 to I to j back to 1, and then fill out with identity matrix, okay? But as it turns out, lots of other bases of permutations. With a colleague, we've exhibited some bases of 1, 2, 3 avoiding. You can find a basis of the n by n permutation matrices, all of which are 1, 2, 3 avoiding. You can find a basis which are all 3, 1, 2 avoiding. You can find a basis, if you know what it means, which are bi-Grassmannian permutations, and lots of other things as well. Next slide, please. Next slide. All right. So since alternating sign matrices were a generalization of permutation matrices, then the convex combination of alternating sign matrices is a generalization of the convex combination of permutation matrices, the doubly stochastics. Okay, like so. So this has been, again, I'm going to not say very much here. This has been investigated. Quite a lot is known about this. This is something reasonably new. Okay, the ASMs are the extreme points of this polytope. The dimension is also the same as the dimension of the convex polytope of doubly stochastic matrices. And there are lots of other things known about this, including a linear characterization of them. Next, please. Okay, this is my last thing I'm going to say now. I guess I'll be finished it. Okay. You can ask for higher dimensional analogs, and higher dimension is become a very important topic. Tensors, multidimensional matrices. Okay. And so let me just say that alternate 3-dimensional, you can do higher dimension, alternating sign matrices have been defined, okay? So a 3-dimensional permutation matrix, I tried to display it there. The matrix on the right is on top of the matrix in the middle, which is on top of the matrix on the left, okay? That's a 3-dimensional permutation matrix. Similarly, if you do the same for ASMs, you also get a 3-dimensional ASM. I just want to say these have been investigated, okay? Next, that's about all I'm going to say. Next slide, please. And that's my talk. Let me just say a little bit about these references here. If you're interested in avoiding permutations, the book by Bona, Combinatorics of Permutations, is very good. I mentioned this Farahad Mirsky before. I've took some pictures out of the Bjorner and Brente book. If you really want to study alternating sign matrices and learn about them, there's this book by Bressoud, okay? Here's a couple of papers of mine that I wrote with, well, one of them is not yet submitted, with Lei Kao. Next slide, please. I've done a lot of work with my collaborator Geir Dahl in Norway. You see 3 papers listed there, okay? this paper, as you see there, that was my first investigation with my three, they were PhD students at this time. We basically, besides working on their thesis, I usually tried, at least in my later years, tried to have a joint project with whatever students I had on a totally different topic. None of their theses were on alternating sign matrices, okay? And there's a paper with Kim there, who is actually a mathematical grandson, PhD, a student of a PhD student of mine. I can't remember whether there's one more slide. I don't know I have anything to say about it. There's some more of that. Okay, there's the Mills, Robbins, Rumsey thing, Zeilberger. Jennifer Stryker has written a lot about the alternating sign matrix. And I haven't given you all the references, but if you're interested in any of these and you look at any of these things, you'll find much more references. Well, thank you so very much. I'm sorry this turned out to be a little cumbersome, but I managed okay. I think Renovia, I think your name is. I can see your name down there. You did a very excellent job. I'm very grateful to you. And I don't know what went wrong here because I've done this before, but this never happened. So good. Okay. Thank you very much again.
Okay, thank you, Professor Buadi, for a very inspiring talk. Let's thank Professor Buadi for the talk.
Just call me Richard.
All right. Okay, Richard. Okay, so before we move to the question and answer session, we will have a small break and I will give the screen to Eddie. But all of you can can think about your question and ask them. You can write it in the chat box or you can raise your hand and you can ask Richard directly the question. Okay, Pak Eddie.
You had enough.
Okay, so now we are going to present some song sung by ITB alumni singers. One of them is Dr. Inovia, actually. And piano played by one of our maestro of Indonesia, Pak Jaya Suprana. And the title of the song is Over the Rainbow.
Well, I'm looking forward to hearing this.
Yes, okay. Is it now? Yeah. Yeah.
To a place behind the sun. Just a step beyond the rain.
Okay. Thank you very much. Okay,
Never been
now.
sworn before. It was very nice. Thank you.
Thank you.
Brady, have you recognized one of the singer?
I recognized her. Yeah, Renovia.
Okay. So if you have a question for Richard, you can write it in the chat, or you can raise your hand and you can ask the question directly. Is there any question?
I gave you a lot to think about, and you may have.
Yeah.
Yeah. It's okay.
Okay, if there is no question, then I will ask
Okay.
Professor Brady.
Professor Wono Setiabudi, please.
Yeah. I think I saw good mathematics presenting by you about something. Maybe people will not do something computing using finding the easiest one, but the structures is more challenging. But my question is only about what can you show me some application of the formula lambda determinant?
That's a good question. And I don't know of any application of that.
Because when
I
you
don't know
compute
whether,
n multiplied by n, then on the right hand side there are many determinants, although the size is 1
Yeah,
degree less than
yeah,
the original matrices.
you know, it's computationally, it's impossible. I mean, it's the summation is over all n by n alternating sign matrices. And as I showed you, even for 4 by 4, there were 42 terms. For 5, it was in the several hundreds. I don't remember the
Yeah.
exact number, but I don't know that there's any computational easy way to do it like there is for the ordinary determinant, where you use elementary row operations, for instance, in order to Gaussian elimination, in order to compute it. So I don't know that anyone, again, maybe I would have to look at this paper again by these 3 mathematicians who invented this, whether they, but that was their original motivation, as I recall, to start with Dodgson's condensation formula to generalize it. And lo and behold, they came up with these alternating sign matrices, okay? It's,
Okay.
I have to admit that I've never really gone through their proof.
Okay. Yeah.
All right. But that's a good question. I don't know that there is any one that's ever applied that in any meaningful way. I mean, combinatorially, I don't know that it tells you anything about ASMs.
Yeah.
I don't know, sir.
Okay. Thank you. Thank you. Yeah. No problem.
Okay.
Thank you.
Sure. One might look at this book by David Bressoud. I told you about the story of the alternating sign conjecture. I haven't looked at that recently. I think the lambda determinant is in there, but I don't think he gives any kind of application of this in any way. But I may be wrong, but I don't think so.
Yeah. Thank you very much. Thank you.
For asking that question.
Yeah.
Okay, thank you, Pak Wono. Is there any other question?
I think our time is up. I'm looking at that.
Just to say, how is Richard?
Yes,
Okay,
fine.
so
Hello.
Sarifuddin. That was
Yes,
the
it's
first evidence.
8:30 evening here. You're probably just getting rid of starting your day, right?
Yeah,
Sorry, I joined a few minutes late because it is 6:30 in the morning that time when your lecture started.
Start at 6:30 there?
Yeah, 6:30 Indian time.
Goodness.
In India.
in India, yeah.
In Kashmir.
Yeah, I see. Oh, hello there, Yari Food and Pizzada. How are you?
I'm fine. How are you?
Fine, thank you.
No.
See you. So that's I see meeting there. Good. Well, this was very nice for me to interact with people from Bandung and other people as
Thank you.
well. And maybe one day I'll get to Bandung, to Java,
Great.
to Indonesia.
Yes.
I don't know. We'll see.
Okay.
We'll see.
Okay. We will invite you to come
right,
to
thank you so
Bandung to visit us. Yeah, to visit Indonesia. Yeah.
Wonderful.
Hopefully
sorry.
next
Problem.
time.
But that didn't happen, never happened before, but something,
That's fine. That's fine.
okay,
It
okay,
works.
all right. so
Okay.
Thank you.
Okay, Pak Edi. Oh, okay. There is one question actually
Huh?
in the chat.
Okay.
I don't see a question if you're at.
Okay, so it's from Nur Hasana. Does ASM of yours could be applied for special symmetric matrices?
Say that again, I'm sorry.
Does ASM of yours could be applied for special symmetric matrices?
Yeah, well, you could certainly ask for symmetric ASMs, okay? And you could certainly, don't number of them. And, you know, I don't know that ASMs in general or symmetric ASMs have any particular linear algebraic importance, okay? From the point of view of linear algebra. From the point of view of combinatorics, because they are configurations with a definite pattern, okay? And you want to study those patterns and you want to enumerate them. I mean, that's what people do in combinatorics in general, right? But other than that, I don't know of any application of these ASMs, okay? Excuse me.
All right. Thank you, Richard. And I think I will give back the control to Eddie.
File, okay. Thank you so much for taking charge of my PDF, okay?
Yeah,
Okay.
you're welcome.
Okay,
now.
so thanks again to Professor Richard Purwardi for a wonderful talk. And
Thank you.
Yes, and we would like to present you some certificates and also some small token of appreciation. Let me share the screen to show you the certificate.
Oh, thank you very much.
So this is the certificate of being plenary speakers in our event. So thank you on behalf of the Faculty of Mathematics and Natural Sciences, ITB. We like to thank you, Professor Purwardi, for giving wonderful and inspiring lectures here.
Thank you so much.
And also, I'll give you a small token of a sketch of your photo.
Hey, are you going to email me that poster?
Yes, yes. We will email you these two
Yeah,
things.
I like that a lot.
The certificate and
First,
also
you
the
accept
sketch of
the sketch.
Very good. Thank you very much. I really like that. I'm going to put that up I'm going to frame it and put it on my wall.
Okay, that's great.
Okay. So thanks a lot. And also I would like to thanks to everyone here. There's a Cyril from Australia. Thank you, Cyril. Professor Cyril Prager, and also Professor Joy from Philippines. And of course, Professor Pesada and all professor from ITB, Pak Mukhlis, Pak Wono, dan semuanya. And also thanks to all the committee of this event. Yeah. So Bu Nuning, Pak Krishna, Bu Novriana, and Bu Rinovia, Pak Yudi, Bu Intan, yeah, Pak Rudi, I should mention all. And then Pak Denny, Pak Ridwan, Pak Yusuf, Pak Irma, Devita, and also Mariani. So this is very good collaboration to deliver this event. So thanks again to everyone who participating this event, particularly from overseas, yeah, and also of course all colleagues and students from Indonesia. Okay, and Pak Richard, we would like to invite you to come to Bandung, yeah, to see Pak Wono and Pak Mukhlis here, yeah. Next time, next year, hopefully you have some time. Yeah.
So what the position of pitchers for the basketball? Pak Mukhlis is always mentioning about this.
Okay, so see you and thank you, and hopefully we can see you again next year. Yeah.
Again, thank you so much, Eddie. Thank you.
Okay.
Thank you,
Bye.
Professor.
Thank you, Dr.
Hello,
Eddie.
Cheryl. How are you?
Serial.
I'm very well, thank you, Eddie. Thank you, Reno. Lovely to see you, Richard.
Okay,
Thank you for your lecture.
Thanks,
you.
Serial.
Thank you.
Joy, thank you, Joy.
Thank you, Pak Edi, Rino, Cheryl, Professor Bualdi, thank you.
Oh, Joey,
Pak
nice to
Slamin,
see you.
terima kasih, Bu Kiki. Pak Mukhlis.
Okay. Thank you, Richard.
Okay, bye now.
Okay.
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 Bye-bye.
Bye.
Bye.
Thank you.
Terima kasih.
Bye-bye. I'm going to leave if I can
Yeah.
figure out how to do that.
All right.
Okay, I'm going to